Bueno, ya se ha empezado la transmisión.
Hello, good morning, everyone. Thank you for coming for this talk. This talk is being broadcasted, and this is one of the training activities that we have in the European project that we have that is called COMETAS. That is basically a project on metamaterials, on function-related metamaterials. The objective of these talks, this is the third talk actually, the objective is just to introduce you to different the research, the project themselves, although we are trying to relate that research to the project, but it's basically to open your mind regarding the possibilities in research and that things that are sometimes may look like being so far apart, as for example biomechanics or cell mechanics and metamaterials, you may think what they are. Why are they linked or why they are related, and probably also this talk Ariel is going to give also some information about that. So open your mind. In these talks, as you know, there are two objectives. One of them is scientific, so we do some scientific presentation, okay? And also there are some soft skills presentation, and those of the skills are in different topics. Okay? Usually, we try to get the experience of the people we are inviting to give that soft skills experience. Okay? Well, Professor Ariel, thank you for coming to the talk. It's a pleasure. And let me present Professor Ariel. Professor Ariel is a professor that comes from Cuba, so to do the talk in Spanish. But this is broadcasted to all the 10 centers of the consortium. So, so he will be in English, and he's also in the University of Glasgow. So right now, I think he prefers to do English also. So, well, the story, I was invited also to the University of Glasgow. I had to give there a talk, so I learned there from his life experience. So that's why I thought it would be good here for the life experience. And well, he changed actually my mind also in one thing, because when I did my postdoc, I had a grant for doing a PhD or a grant for doing a postdoc. I already was a PhD in Spain, so at that time I thought, okay, that it would be stupid to do another PhD, no? Because okay, I already have one. But probably the experience of Ariel will show you that I was short-minded. No? So really, you should look at life as a life experience. So it really doesn't matter if you're doing a PhD or you're doing a basically if you're doing research. And the other things are mainly a way to pursue your research, academic research career or your professional career. So you have in life to be open-minded. You have to be, let's pursue your goals, but also you have to be open-minded. So I think that Ariel is going to give us also some experience on that. We were discussing just before how to do the presentation, so I think that best is that instead of being at the end of the discussion, he wants to put it in the middle, that is better.
So, yeah, and we can in two parts.
So okay, so again, so thank you very much. I give the stage to you, and thank you again.
Thank you very much. Thank you. Okay, so thank you very much for coming. I know that some of you should be here because you have to be, and I hope it's not too bored for you. What I'm going to speak is a little bit far from what you're studying right now, even though there should be some similarities you could try to realize we can have. So the idea is to present you some work, how to model some biomechanical problems, and we use for that continuum mechanics. So at the moment, continuum mechanics is having a lot of success in modeling biology in general. So what you're learning now can be also translated to that area. So I'm going to divide the talk in two parts. The first one has to do with a technique which is called asymptotic homogenization and is widely used in engineering for example, trying to figure out the best properties you can have when you're building something. In this case, we just want to realize what the microstructure of a biological tissue is doing to its overall properties. And in the second part, please go to the room. The second part is going to be related to a different kind of homogenization approach in which we don't look at the microstructure, and in some way we know what is happening at the macro scale, and we just work with that and see what are the advantages and disadvantages of these two approaches. Okay, so I don't know if I said it, but thanks, Paco, again. I just forget if I said it or not. Okay, so this is the part one, and I hope you can see there. Okay, so I have some issues in my eyes, so I don't know. But this is a paper we published recently. Well, not recently. This is in 2018. Still have a lot of open questions. So I like to present in a lot of conferences I go, and I enjoy doing that. So the idea, what is? So you have a biological tissue, and you want to try to figure out what is happening. No, you want to study how it evolves and try to obtain from that evolution what could happen to that tissue. For example, that is useful if you are in tissue engineering. So you want to replace a cartilage, and you want to construct something that biomimics that. So the idea is to use these properties to construct that material then that your body could assimilate and has the same structure and functionalities as the original, the one you were born with. No? So one of the complexities of doing that is that this kind of, the tissues in general, biological tissues, are active. So they are always trying proliferations of cells there. If there is damage, they are trying to to heal in some sense that is damaged. So, and from the mathematical point of view, modeling that is very difficult. So that is not an easy task, and there are a lot of open questions at the moment. So we are trying to put more models, more complicated models, and trying to figure out how to solve that kind of issues that could be have an impact in engineering. So what is the other issue is that when you think about biological tissues, they are highly heterogeneous. So, and the microstructure is quite difficult to represent in a computer. So we have all these numerical methods to try to represent the microstructure, but it takes time, so it's not easy. And here, for example, the picture on the right, you have a bone, the internal structure of a bone. That so on the left it would be the healthy one, and on the right you will have some that the same part, but with a disease. In this case, osteoporosis. So that means that the bone lose density in that sense. So you have to take into account, if you want to model this disease, how it evolves, you have to take into account how the material is losing that density in that case. Okay. So there are other examples, not only bones in biology. You have the multicellular spheroids, in which you do some kind of experiment, and what people see is that the internal structure of that tissue is changing, and it has a change that remains. So if you let the tissue and remove all loads or the experiments you're doing in it, it will maintain some internal structure that will be different from the one you started with. So this kind of behavior remembers what plastic material do. So the idea of biomechanics is to take those concepts from plasticity and trying to interpret them in the sense of biology. And in fact, this calls for the introduction of new kinematic descriptors that are trying to model what is happening inside the tissue, but independent, at least virtually, of what is happening at the macro scale, not the things you can see. The picture on the right, this is very difficult to see, but on this first line, in red color, there are some small lines that are representing fibers in a plant. Okay, so something you find now if you go out this building, and there are indications that the reorientation of these fibers also have a mechanical, how do I say it? Explanation. So the idea is to try to bring mechanics to develop some model for this kind of behaviors. Now, you are first year, second year, third year, fourth year. So have you seen some mechanics? Yeah? Okay, so you should be familiar with these conventional notations in which you introduce the configuration of the body, you introduce the motion, the deformation gradient tensor to see the changes in shape of the material, and then you have all these concepts that are classical there. So what we do in this case is to bring a concept from plasticity, which is to decompose the deformation gradient tensor into two contributions, one which is of elastic nature and the other has a plastic nature. And there on the right, there is some schematic of what is going on. So the idea is that if you take your body in the current configuration and you remove all loads, okay, you remove all forces acting on that material, it will go to some kind of, you think, to expect to arrive to some kind of a stress-free configuration because you removed everything. But what happens with, for example, biological tissues is that that is not the case. So they will still have some stresses inside that we call residual stresses because there are changes happening at the internal structure of the tissue. So we do that, we represent those changes through this tensor here. It says that gamma, it should be FP in the case of plastic-like distortions that we want to use here. And then you accommodate those parts with the elastic deformation gradient tensor. Okay, so the idea is to split the contributions that are purely elastic and those that have a plastic nature. Okay, so if we speak about remodeling, which is the case we'll be bringing in this first part of the talk, one thing that we don't want, or at least to simplify things, is not let the tissue to grow. So that is a property that tissues have. So bones grow, so we grow on the one age, and then we go down. But the idea is that we want to remove that, at least for keeping things simple. And that is done by asking, so you know that the J, the determinant of the deformation gradient tensor, allows you to see changes in volume. So in this case, the way of saying we don't have any addition or removal of mass is to take the trace of the plastic grade tensor to be 0. So that means that JP is equal to 1, which is the determinant of that kinematic descriptors. And another simplification we can do is to say that the skew-symmetric part of that tensor will be 0. So we avoid rotations, kind of rotations there. It's just for simplicity. It can be done. It can be allowed to do that, but just for the time being, equations are simple if we avoid that kind of situation. So what are the kinematic descriptors of the model we want to develop? So one is the motion. We have the deformation gradient tensor, which is a derivative. So we have a theory of order 1 in the motion chi. And we assume to have another kinematic descriptor, which is the one trying to keep track of those changes at the microstructure, which is the tensor FP. And in this case, we have a theory of order 0 for FP, even though it could be generalized. So you can introduce the gradient of FP to resolve other kind of situations that could happen in biology and in general in engineering. So our idea is to maintain the focus on these three kinematic descriptors. So we need equations for our model, and usually you can use the principle of Richard Powers or Richard Ward to have the dynamic equations of your system. We use some of the papers that you can find in the scientific literature, which is extend the principle of Peter work to allow to have some generalized forces, which have the nature of the microstructure of your biological tissue. And by localizing, we have two kinds of equations. So you may recognize the first one. That is the the balance of linear momentum, where P is the first biological stress tensor. And here we are neglecting inertial terms and body forces. So these are kind of assumptions to maintain the model simple. And we have a balance of forces, internal and external ones, conjugated to the plastic strain. Once we have the equations, we want to be at least thermodynamically correct. So we use the dissipation principle to get some constitutive information about what we are doing. And what doing this approach, what you have is something called a survey. So this could be recognized if you have done this before. So you have the first biological stress tensor can be written in this way. So once you have your strain energy density, in this case we're assuming it's hyperelastic the materials we have, you can compute the first biological stress tensor and you can solve the model. To describe, so to find the evolution equation for these plastic-like distortions, we have the second part, which introduces what is called the Mandel stress tensor. And in theories of remodeling, what happens is that Z, which is that external force, could be assumed to vanish. Okay, so it's zero. It remodels because it remodels. There is no need to an external component for doing that. But for example, if you are trying to develop a theory of growth, you can assume that this set is the one making the coupling with chemomechanical terms. For example, imagine the growth of a tumor. You need nutrients, so that tumor needs nutrients to grow. So you need to input that and how it relates to the mechanics of your model. So Z is the one in which you can input this kind of terms. So, doing some simplifications and some assumptions, you can find what would be the equation for the evolution. So here there is a time derivative of the plastic-like distortion, so the evolution of the internal structure. And we made some assumptions in this case, mainly because we use this technique, which is called asymptotic homogenization, which is already difficult to solve, and we want to maintain things simple. But which means that gamma here is a constant for us. But you can do things more difficult and more realistic, because that gamma could be written in this way. These are called Yershina-like models, which means that remodeling starts when you have a yield stress. So this is when just your material start remodeling. And that could be coupled with, in the case of tumor growth, with nutrients. So when your proliferations of cell, for example, is like that kind of behavior, and you need nutrients to start that mechanism. So that means that in this case, this is our model. So the first part of the talk is just to say where these equations come from, because the first one should be familiar to anybody that has done some continuum mechanics, but the second one, no, is not that standard. So what it means. So we now go to the case of a material which has two constituents. Now we don't have a specific application in mind. It's just to have a proof of concept of what this kind of modeling, what kind of information this kind of modeling could be. So what that means, that we have two kinds of materials, both of them hyperplastics. They are interacting between each other. And we want to see if we homogenize. So we have this heterogeneous structure if we look with glasses, and then we want to see what is happening at the macro scale. What I see, for example, in this table, I don't know what is happening inside, but I can see this. I want to come from inside with this mathematical technique and see how that affects the evolution of your material at the macro scale. Okay, and this could be in any. This kind of approach can be used in any engineering application. So you can use this asymptotic homogenization for constructing a material for a rocket, because you need it to have certain properties. How I construct that? What is the kind of geometry I need for the materials inside. What material? I use carbon, I use metal, what kind of metal. So what is the one that will give me the properties I would like to have, no? Like an inverse problem. So we are doing that, but in the sense of biology. So we want to see the evolution, no? If we want to treat with drugs, how will respond to drugs? If we want to replace certain part of the body, what the properties that should have, what kind of material I need, how I print that, what geometry I need for the microstructure, all of that influences your selections. Okay, and this technique gives you that information. So that is the idea. So we have a balance of linear momentum for each material. So we see them as a continuum, both of these constituents, and we have the same equation for the evolution. But what we are going to vary are the constants. So these material properties. So John modulus, for example, we can have one higher than the other, or bulk modulus, things like that. Okay. So that is the main idea, and this is what homogenization does. So we have this heterogeneous. So this is a schematic, not a very good one, but the main idea is reflected there. So we don't want to see the microstructure. Why? Because computationally that is very expensive to solve. So we don't want to do that. We want to replace that heterogeneous structure with an homogeneous one, but we want, in the replacing, we want to maintain the properties somehow. We want to have them in hand. And the technique has been used in nanomedicine, biomaterials, tissue engineering, and engineering in general. Okay, so it's very old technique. And what we are going to do is to exploit that information on the microstructure, and we are going to cipher. So that is the word. We are not going to keep the geometry, but we are going to cipher all these geometry mechanical properties in coefficients that are what are called effective coefficients in the theory of homogenization. What that means? So mathematically, how we describe that? So we need a separation of scales. So we need to have a proper microstructure and a macrostructure. In the case of an effective, an active material, those length scales could change because you are evolving in time. So this, in a mathematical sense, we take the supreme of all those scale separation and assume that they are less than one. Okay, so they are well separated, is how we say. So what that means, it means that if you see a field, any field that you can have, displacement, stresses, things like that, can be written in a two-scale fashion. Okay, so introduce two variables which are formally separated, x and y. X is called the macro scale, so it's how you walk in the tissue, what you see, and the y is like the sum you do to see what is happening inside. Okay, so these two variables keep track of that. And that means that when you see a partial derivative in space, you can you use the chain rule, something that you learned in first year, and you have that decomposition, which has a lot of implications. And the main idea of homogenization is that you can write formally an expansion. Okay, so think about type Taylor expansion, things like that. This is different. This is just you assume you have an expansion for that field, and you want to find the components or the elements of that expansion. Okay, so that is the main goal by substituting that expansion in the original problem, which is this one. Okay, so what we want to do is to construct several sub-problems, and each of them will give you some kind of information of that we want. So what are the main assumptions here? These are the classical ones. The classical assumptions is that we have periodicity. It's not the real one, but it's the one that allows us to do real computations. It doesn't have to be kept. Okay, we can disregard that and we can solve problems, but at the moment, you can only use it in very, very, very simple problems. So for us, which are dealing with a complicated one, we assume that we have a periodic microstructure. Okay, and we also assume this, which is called macroscopic uniformity, which means that the same structure repeats. So one for the field, okay, and then we have the structure, and we have, for example, this is an enclosed. So think about a fiber reinforced material. So you have inclusions, you have a matrix. So that means that if you choose one piece of the material, if you go to the microscale, you will see the same thing repeated all over there, okay? And those are assumptions that, for example, help us to swap the differentiation and integration operators. Things could complicate because we can say, okay, we don't want periodicity and we don't want macroscopic uniformity, and that could be very useful for metamaterials, for example. And what happens? So from the mathematical point of view, if you average, which means if you do an integral and you want to swap the derivative with the integral, you need to take into account a sort of Reynolds transport theorem. So you need to keep track of what is happening in the movement of the inclusion. Now you can have an inclusion that grows with time, for example. Okay, how you keep track of that? How you rewrite periodicity if you have periodicity in terms of that expansion of your inclusion. Okay, so these kind of things can be done. It's very difficult. Still, we are working on that. So we go to the first case in which everything is nice, periodicity, macroscopic uniformity, and so on. But the main idea here is if you in the future are interested in asymptotic homogenization, like a lot of engineers are, and here in the group of Paco, there are people doing that, this can be done. So you can open your minds and go where nobody has gone before. Okay, so we come back to our problem. And what is the idea? Remember, I say when we go with this homogenization technique and we put the expansion in the original equation, we start equating in powers of epsilon, which is the smallest parameter. And we have a class of subproblems for each epsilon, okay? And you decide when to stop. And that would depend on how good your solution would be, how the approximation, if you do some numerical techniques, you know that when you do an approximation, you want to reduce the error in which that approximation is far away from the analytical solution if there is, okay? So we stop at epsilon 1, for example, in these kind of problems, which means, so these are the expansions, okay? I'm not going to this, just to have a look of what we are doing. And what is happening is if you stop at epsilon 1, you have two kind of problems. One is called the cell problem, and that is for a reason, because it's the one that will give you all these properties of the microstructure and will put them in what we call the homogenized problem, which is the equivalent one to the original, but written in a homogenized domain. So you don't have to take into account in your mesh of your numerical scheme, you don't have to take into account of the real microstructure. That is encoded, it would be encoded in this problem, even though now it's not that obvious. And solving this problem will give you a very nice approximation of the original solution. So you can do that. So the main idea is to go to the computer, represent the chaotic internal structure of something. In engineering, that is not chaotic, but in biology, that would be the case, okay? And then you would like to also homogenize, this is how we say, the evolution equation, okay? So you want that also at the macro scale. The good thing in the formulation we are having is that we don't have a related set problem. And that's why we have a theory of order 0 in FP, okay? If we would like to go on and assume higher order theory, for example, when you have cracks, that is you have non-local phenomena, that is a good way of going and adding a derivative. It will complicate your model, but it will allow you to solve another kind of situation. And this is how it looks. I don't go through the equations. My idea is always, when I attend a conference, sometimes the equations, I don't get what is going on there. So I try not to speak too much about the equation, just what they are representing, rather than the form, the structures they have. Hopefully, you can follow me. I know it's difficult. Sometimes for me also, it's quite difficult to explain all of these things because there is a lot behind that I cannot say here. So it takes we need to do a course to know what is happening there. But I try to be as simple as possible in explaining these things. Okay, so now we have the equations, the ones we have, we would like, and now we need what kind of materials we are dealing with. So we need the constitutive law to start. And when you're doing mathematics, you say, okay, let me do simple because it's difficult. That is not easy. Sorry. And so for us, we took for this time being the Sanvenant, which is the more something near to linear elasticity, okay, but still non-linear up until this point. Later on, we are going to simplify again. You will see a lot of simplification, and still the equations will be quite difficult to solve. And there are a lot of definitions there, but the main idea is that we have the constitutive law, and we have the Green-Lagrange strain tensor, the Ricochet-Green strain tensor, or the elastic counterparts. This is how you write the elasticity or stiffness tensor if you have an isotropic material. Okay, so this is how we can write it in terms of two parameters. Kappa is the bulk modulus and mu is the shear modulus. Okay, and there are definitions on how we would like to see these first order tensors. Okay, so we need to homogenize that. So that would be, we need to expand that as a series, okay, and take the leading order terms. So this is the one that I call with 0 to have the homogenized version of that. So we choose that elastic energy because it remains quite nice when we do that expansion. And using that information, we can compute the second order Kirchhoff stress tensor. The second theoretical stress tensor, which is going to look like that. Now, the issue here is that we want to solve this in a computer in some sense. And at the moment, this nu, which is written there, means that that tensor is defined as you do in calculus or functional analysis. I don't know how you call it here. But the idea is defined in a domain we don't know how to represent, which is that middle domain in the schematic I showed at the beginning. So what we like to do is to pull back that information to the reference configuration. So we want to do like a change of variables in some sense. It's not that bad. The main idea is to put it in a domain we can represent in a computer, and it's not difficult for the computer to solve it, okay? So that can be done. And this is the one that we call CR, R of reference. And that would be the elasticity tensor in the reference configuration. And this would be the leading order term of the second order Piola-Kirchhoff stress tensor. Now, one thing that we can notice here is the following. So if you took continuum mechanics and you have some elasticity courses, and you did in physics or whatever, because you use the, what do you call it in English, el muelle, you have Newton's law there, so you know you have an elasticity constant there acting as the properties of the material. Here instead, we have these tensors Vp, which are metrics induced by Fp. So they are defined like this. Okay, so it's like the left Cauchy-Green tensor that you know in continuum mechanics, but now we are in that with the classical counterpart. So what that means that if you look at this, if you read this equation, it means that your elasticity tensor now is changing also because your internal structure is evolving. Okay, so your material properties will change because there are changes occurring at the microstructure. So that is the main idea of that equation, and then we have some definition just to be consistent. Okay, and now we're going to simplify again. Once again, we simplify, because still it's difficult to solve. And so my formation is as a pure mathematician, which I became impure in some sense. But I prefer to use software to solve my models, no? So I don't have the expertise like here you have in finite element methods. I can use something, but I cannot do my own software. Let's say I would like more to focus on the theories, like a path, what I like to do as research. So if I want the software to give me a solution, I would like to give it like a baby, the food, spoon, open your mouth, take, and give me the solution. So we're going to simplify in this way. So we are going to assume that, so imagine as a bone, at some point our bones stop growing, because we stop. And we are going to assume that we linearize in the deformation gradient tensor, which means that the shapes that we can see now are linearized. So we have a linear structure that would be here. So the formations are very small. But still, we are going to maintain the fact that the plastic-like distortions are nonlinear. So this is a nonlinear framework there. Like if you have a disease, something is happening inside the bone that is still is doing something, and the deformation are not small. Okay, the plastic-like distortion, so the inelastic distortion, we say. So if we do that, it means that the deformation gradient tensor can be decomposed in this way, where H is the gradient of the infinitesimal displacement, which in a two-scale approach is like that. So we need to take into account the expansions we did at the very beginning. So what that means that now here should be a P, not a T. Forgot that. So it means that the linearized version of the first Viola-Kirchhoff stress tensor has that form. And then we can do some things to solve the cell problems. Remember, we started there. We are just creating the background still to put it in the equation. And one important thing is that this elasticity tensor, CR, will maintain the symmetries we started at the beginning. So major and minor symmetries that we assumed at the very beginning, even though we have the evolution of the material, okay? For each constituent, we still need to homogenize that. Okay, and now things get complicated in reading, because this is how the cell problem will look like. So the one that will give you the information of the microstructure. Usually in homogenization, you assume, so you know that the solution exists in a mathematical term, and then you say, okay, I know there is a solution, let me try one. And if that is solution, then I found the solution. That would be the way of thinking. So in a linearized setting, we can use this kind of writing. So what that means that the cell problem, instead of finding U1, in this case, that would be the initial unknown, we decompose that problem in two subproblems and to find a third order tensor, which is this side, and omega, which is a vector in this case. So each of them will contribute to something inside the tissue, the material we are working with. So if you look at the first line, so this EP0 is the plastic-like green Lagrange tensor, so it depends on FP. How we say we don't have remodeling, or we don't have this kind of material evolution, we say that FP is the identity tensor. If we say that FP is the identity tensor, what will happen is that this term will disappear, and that term will disappear, okay? And this equation here will be a trivial one, will give you a trivial solution. So what that means, that this vector omega is the one keeping track of what is happening inside, and is coupled, because we have a couple between elasticity and plastic-like distortion, with this one that will keep track of that elastic nature. Okay, so you have the two contributions in those encoded in these two unknowns that we need to find. If you continue, then you have how the starting balance of linear momentum looks like. And now there is something unusual here that you should expect, but it's not what usually you find, which is the introduction of this term. So we started with no forces, no inertial term, no acceleration, no body forces like gravity, things like that. And then we found that something is coming here. And if you look at the definition, you have omega, EP. So if we don't have remodeling, which means that EP disappears, this term disappears, and this is a trivial one. So that means that if you don't have remodeling, this term doesn't exist. So this exists only because you have this material evolution. So you can go to limit cases if you have this kind of situation to test your model. No? If you then work in industry or you follow academic career, you would like to see what happens in limit cases, because that gives you an understanding of what is going on in a simplified case. Before showing you that, let me just say, okay, in that linearized case of the deformations that we can see, the evolution equation has that Fourier form, which you have all these tensors, fourth order tensors, second order tensors, so, and we need to find the solutions, we need to put the solutions there, we need to find them. So it's difficult to solve. Okay. So the simplified version. Let me see. Okay, so something very important here from the computational point of view that you may be interested is that at the macro scale, you see the contribution at the micro scale through these two. Well, this would let me put it there. I need to find out. Okay, it's here. So you see that we are feeding our problem at the macro scale with microscopic terms, but this one here also depends on what happened to the macro scale. So we need to go down and inform to the micro scale what is going on in the other side. Okay, so you have this talk between the two problems that you need to solve at the same time. So that is very difficult to do. And what happens if you go to a limit case? That disappears. So if you don't have remodeling, which is the one acting as the link between the two problems, the cell and the homogenized equations will decouple. Decouple in the sense that you can solve one independently of the other. You only need to feed the homogenized problem through the solution of the cell problem, but you don't go down again. So you solve at one level, you use that information, put in the other equation, you solve it, and that's it. Okay? So that is the main difference. And this would be the limit case you would find if you would have a problem of linear elasticity in which you have a composite. And you want to see if I use metal and wood and I combine them, what would be the properties of the whole material? Okay, so that is the main idea. And so here there is a very simple example in which you can find this is how the elastic tensor, the elasticity properties will look like if you want to find the homogeneous ones. Okay, that would be that expression. So you have a very nice analytic expression. You have a linear material. So one material, you attach another one, you attach another one, not the same, but in a periodic way. And you can solve that equation analytically. You don't need a computer for doing that, and you can find that expression. So give me two materials in this arrangement, and I will give you what would be the property. Okay, idealize, because we could have some contact problems there. But if the contact is ideal in the sense that it's perfect, I can give you what the property without you doing the experiment. You don't need to do it. This here. Look, this would be. You can do the experiment then to corroborate. I did the computations right, but they should coincide in some sense. Or if you have more complicated geometries, you can use finite element methods. This can be constructed in the one hour by the group of Paco here, so even less. And this is how the formulation will look like. This is just to put the formula to relate the mathematics. So as a mathematician, we will only relate mathematics to what we are seeing. And the idea here is to tell you, you can do this if you're interested in. And it's part of the research we do every day in some sense. Okay, but now we have the complicated problem in which we have remodeling. And what that means. So imagine this is your macroscopic domain. So you don't know what is the microstructure that is encoded already. So you need to solve one different problem at each microscopic point. So imagine this mesh. For each point, you have a different problem to solve. That is very expensive. You have to translate the information from one side to the other in a time-dependent way. So doing all of that is not trivial. Okay, so one needs to spend some time at home, at work, and don't go anywhere else. So 0 parties, let's say, would be the case. And this is a benchmark problem that we use for that because we have this paper and the reviewers say, okay, everything very nice, but give me some graphics. And sometimes that would be the case, no? At least in this, as mathematicians, sometimes don't want to, but real life says you need to convince people, no, what you're doing is correct in some sense. So let's just take the same structure that is very nice because we could do some analytical things there. The other important thing is that since the variation is only in one direction, your three-dimensional problem can be just described as a one-dimensional one. And that is a good thing. So we took two different materials, isotropic materials with some values of lambda and mu, the Lamé parameters. We didn't think of a material specific, you choose at this point some values just to test the model, no? In this case. That is a drawback. Of course, one wants to do some real life thing, but it's very complicated. So we need to start with a proof of concept. And we assume this specific form for the plastic light distortions. The main idea is that at least without any other information, you need to be aware that you need the determinant to be 1 for all points. So you need to construct something in that way to avoid growth in some sense. And what that would mean, as we expected, that our elasticity, the pullback of the elasticity tensor depends on the mechanical properties of the material you are constructing, let's say, and on how the evolution of the internal structure is affecting the properties. Okay, like in bones, no, less density, and that kind of situations. So this is just to show how the cell problems reduce in form. So they were complicated. Now at least we can read something there. We have only a derivative. We don't have all the derivatives, and we need to solve that. Still, analytically, we cannot solve it. So we need to resort to numerical methods in that case. And this is how the homogenized balance of linear momentum will look like, and the evolution of P in this case, no? Which is the parameter that we are using to represent FP, so like spherical tensor. And we prepare our experiment, numerical at least, and so we have one Dirichlet condition to be 0 at one end of this bar that is has a layer structure. And on the other side, we are going to put a loading ramp. So we are going to extend it in time, okay? And we're assume an initial distribution of P. So these kind of things is information you can obtain from experiments. But in this case, it's a proof of concept. We don't know. I don't know how to do an experiment. I cannot enter a lab. I will do a mess there. But the idea is that you can do this from experiment. Okay, so an initial distribution that will tell you how that will evolve. These are some graphics of, we'll try to explain what we are seeing there. So the yellow line, the one in the middle, that is how, what would be the elasticity using flow notation, which is C33, so it will be 3333, some one property of the material. And in that case, it's a constant in space. Why? Because if you don't have the model, you're going to have variation in time of that elasticity, effective elasticity. But if you assume that you have the evolution, that P is evolving, you have an equation, you have a time derivative telling you how it's evolving, then you see how the properties of the material will change at each point. So you don't have a material with the same Young modulus here and here when we do the test. We have a material with different Young modulus because we have something happening inside for some reason doing that job. Okay. I will skip this one. This one has more information probably. So this again, the solid line, it would be the solution of the elasticity problem, the homogenized one. And you see it is a line, just a line, because of the boundary conditions that we used, and that is how it looks like and can be computed analytically. Instead, if you put the solution of the one with remodeling, which is the dashed line, you see how it changed now. Why? Because at each point, the property is different. Here is different, here is different, here is different, here is different. So this is reflected also in your displacement. It's not longer that line. So now you have something else. And this could be useful, for example, you have an experiment, you use the theory of linear elasticity, it's not working, what is going on? Because probably you have this kind of distribution. You say, oh, let me try this. And then you try that remodeling aspect and you say, now let me match what I obtained from experiment with the model I am doing. And I see they match. Oh, okay, so there is something happening inside that I can explain. Okay? So this would be the first part of the talk. To breathe a little bit, let me tell you. So the first picture you should recognize if you have been there. So that is Havana in Cuba. Very nice in the picture. And it's very similar to Spain. No? It was built by your ancestors and some of us. So there I did my PhD, the first one at least. I did my bachelor, master degree, and PhD with the same person, which would be Reynaldo Rodriguez Ramos, that has been here, even though you haven't seen him. I won a postdoc in Mexico after I graduated, so I changed country, something that you should be open to if that opportunity happens, could happen. Mexico is very nice because you are living between an active volcano. Every day there is an earthquake. Mexico City have 20 million, maybe more people. So like this, so it's stressful. It's not. It's very nice as a country. It's a very nice country. I enjoy a lot being there. I fall asleep during an earthquake. I didn't wake up, so it could happen. But yeah, it was a very nice experience there. Then I moved to Italy. I had two options. I could have been here or with Jose Merodi, or I could move to Italy. Don't ask me why I chose Italy. It was intuition. I don't know. It was like that. There was something. I could spend more years doing research there, and that would be a factor that I weighed in my decision probably. Touring is where General Motors is, Fiat, Ferrero, so it's not very bad. It's nice to be there. And you have the Alps, I don't know if you can see them here. And this is the National Museum of Cinema in Italy, at that point. So I spent there, so I arrived as a postdoc. So this is part of the soft skill, probably, and then you can ask me whatever. Yeah, I arrived as a postdoc, and then my life turned around. I started again at PhD. So for several reasons, life sometimes, or because if you're in academia, you will know that opportunities don't come that often. So we need money, and that would mean sometimes there's no money. So the possibility there was that one, and also because I loved that group in which I was working with. I will show you the pictures later on. After 2 years of starting the PhD, so I took like a step forward, backwards, let's say, in the career, but it allowed me to put two in front. I always say that. So even though it was not a very usual decision, so you don't go to do a PhD after you have a postdoc. That is not normal. That is very unusual. And then I went to Glasgow. I tried to put some picture that at least could relate to engineering, because Glasgow is an industrial city in some sense. Even though I don't know what that serves for. Don't ask me, I don't know. Maybe it's because of boats or something, probably. But yeah, that is the only sunny day in Glasgow in the year. That picture, once a year they take a picture of Glasgow and they put it in the internet, because it's always raining, it's cold. Paco could tell you that. It's very windy, it's very, very windy, but people are very nice there. And the University of Glasgow has a high ranking, so it's a very good university in UK and worldwide. So it's a very nice department there. So the picture, so these are the grants I always like to say these are the grants I help me to. So if you remain in academia, you need to apply to grants and scholarships and things like that. So you need to remember that people allow you to do that in some sense. Don't forget. So this is Renato. This guy you could recognize is here in front of you. I don't know if. So they were. This is my national supervisor of the PhD thesis, Jose, who was the international one in that case. This is Enrico Sabina, who was my mentor in Mexico, and then Luigi Preziosi and Arco Grillo. The first one was my first postdoc in Italy, and Alfio was my mentor, PhD advisor, so he's a very important person in my life and in my career at this stage. So other two persons that are important in my career, you can recognize some person there. Is Salvatore De Stefano, is researching in Italy. So the idea here is like, if you're in academia, you need to work your way around and meet people. You need colleagues. Now you cannot work alone. If you work alone, you're isolated. Unless you are a genius, you won't advance. And if you are a genius, maybe neither. So you need people around you, good people. This is Raimondo, the one you don't recognize there, who was here, actually. He did a postdoc at the Polytechnic of Madrid. So he loves Madrid. He always, la movida madrileña, he always tries to remember with pain in some sense, because in Glasgow we don't have that. Well, this is just to tell you, if you are around good people, that will work. Okay. So, end of the intermission. We come back to the mathematics, and then you can ask me more questions, and I can speak more. It's just to take a break. Now, this second part is about how you can use non-standard approaches to derive new descriptors in some models. And in this case, we were interested in seeing how a non-standard diffusion, so you know what diffusion is, okay? And which is usually a fixed law of diffusion, that would be what I call a standard. And what happens when the kind of diffusion don't explain experiments, what you do. So you need to move to or you remain there and you say, okay, they are good enough to do what I need to do, or you can just turn on the modeling part of your brain and say, let me see what I can do in that case. So the motivation is that there is a lot of interest in biomechanics about how a tumor grows. There are, for example, treatments that have been projected because of the information mechanics have provided. Okay, so it's not something we do just for fun. The idea is sometimes it's fun, but the idea is to go and try to do something in the real life, even though sometimes it feels very far. So our idea is this third point. So fixed law sometimes is inconsistent with some experiments, and that is why we have heterogeneity, and we may have some hierarchical structure of biological tissues, in which you go through the scales. That's the first picture I showed with the bone. So we have a lot of scales happening there. And there are experiments, for example, in cells, when you put a protein and you follow the path of the protein, and you try to do this kind of graphic, which is the mean square displacement versus time. If the relationship is linear, it means that you have a standard diffusion, and that is the fixed law. If it is non-linear, so it deviates from that line, then you have something that we call anomalous diffusion, non-Fickian diffusion, so there are several names. And here you have the colors of what is going on. So you have super diffusion, or you have subdiffusion, and this is done also with the movement of species of whales, sharks, or elephants, whatever, because they sense something and they go to that place because there is food and then remain there and eat the food, and then they sense something and go other way around. Also, cells have that kind of behavior. No, it has been proved in experiments. even though fractional calculus is still not well accepted, still it's old but not good enough with respect to experiments. So what that means that we would like to model non-locality and how non-locality is modeled. So you can use higher order derivatives. Okay, it gives you some sense of non-locality. So if you take your definition of limit, a derivative is a limit at the end. So you work with a neighborhood, and you can extend their neighborhood in some sense by adding higher order derivatives. But it's limited. No, you cannot go too far away. So what one does is to go and introduce integral differential operators, because the integral, if you know, you go from point x0 to point xb. Okay, so this is a way of accounting non-locality. So what happened in xb and how that reflects in x0. And one theory, which is very, very old, but now it is in fashion, is fractional calculus. So it means that you take derivatives and integrals fractional order. So the pi derivative of a function, what that looks like, instead of only a real number. And that kind of tools are being used, for example, explaining non-frequent diffusion in some simple cases. So our goal is to use that to see what, if we have a non-frequent diffusion of nutrients in a tumor, how that affects. And you can think as a application, we have a drug. We want that drug not to go through all the body and being destroying everything in its path. We want to go to the tumor where it needs to go. So you want to model that. And when you go through a tumor, you have a very tortuous chaotic environment. The veins are like tortuous. Sorry, repeating the word. And how you take into account that? Because if you have the particle, it will stop at some point because the path is not linear as you would like to get the treatment done. No? Something like that. You want the drug to go to the place it needs to go in an optimal way. That is the main idea. So here we use a different homogenization approach, which is what is called mixture theory. And it forgets about the microstructure. We don't care. That is not our issue. Why? Because equations are simpler then, and we can solve nonlinear theories and in that case. So that would be the advantage and disadvantage of these techniques. So in this case, we have, so imagine you have a solid and a fluid phase, like a porous medium, and then the solid phase for us is just the combination of cells that proliferate and cells that die, because they are necrotic, as you have in a tumor, you have necrotic regions, because the nutrients are not arriving there. And in the fluid phase, we have chemical agents. This could be whatever. We just need to put a name. And in our case, was nutrients. Okay, so the dynamics will follow that of nutrients. And we have water. Just this is the kind how we model this avascular tumor. And then we use again the same theory that I presented before, but now F gamma is going to represent growth. It's not going to represent. So it's always something happening inside the tissue, but now it will reflect in growth, okay? Not in change of. Material property. Even though it could. In which you take this asteroid, multicellular asteroid, you remove all forces, you don't apply any load, and then you open the tumor. And you will see that the tumor will, like a flower, it will open in this way. And that happens because inside the tumor, there are forces, stresses still active, not because of the loads you had before, because there is something happening inside, that proliferation of cells, for example, reorientation of fibers. So there is that characteristic that you should take into account for modeling growth. So this is how that decomposition works. So it splits the contribution because of growth, because you can see as a deformation that there are two things happening there. There is growth and there is deformation. So we split those contributions independently. Now, there exists the mass balance equation. Usually you see it as conservation of mass, and you don't grow. But in this case, we need that the constituents that we are dealing with, they change in time. They grow, they exchange masses. So I give you something, the nutrients enter to the cells proliferate, so you create more mass of solid in that case. And if you die, you need to go to necrotic cell, become necrotic. So we need all these dynamics to take them into account. And you do that by writing the mass balance law. And instead of zero, which is as you usually see them in continuum mechanics, you just use rates of sink of all sources of mass. And that is to get this interaction between constituents. So, as I told you before, we usually go to the reference configuration because if you want to solve a problem, if your configuration is changing, you need to keep track of that change if you are in the current configuration. But if you are in the reference one, you don't have to. So you have a fixed configuration, you solve everything there, and then if you need to do a push forward, and then you get the fields as they look like with the change. Okay, so this is like a computational tool for solving the problems. And this is a rewriting of the same equations we had before, just that. So one for the proliferation cells, they are related to the necrotic one, so we can do another equation. This one is because we assume that that times ref gamma, I don't know if you saw the gamma there, is spherical, so it's described by only one parameter. We could have more general cases, but why to complicate things? They are already complicated, and our focus is a different one. We want to see another kind of situation. And then you need the dynamics, so the balance of linear momentum. In this case, this is how you average in this linear theory. You add together the stress of the solid phase and the stress of the fluid phase, while in homogenization, you had a lot of contributions from the microstructure to describe that. Okay, so this is why this is simple in that case. And this is Darcy's law. You can recognize it. This is permeability. Then you have the pressure. And they look like this if you go to the reference configuration, if you do a pullback of your fields. If that happens, then you need to say what kind of materials we are dealing with. So the constitutive expression. And in this case, we choose one from the literature, which is by Holmes and Mao. So they did experiments in soft tissues, and this is the one we use for that matter. And we do it to compute the derivative of that experimental function, so we need to do a lot of computations there. I don't do that here because I don't think it's needed. And then we can also describe the permeability in this way. Okay, having taken into account volumetric fractions, the change of shape, the load, some material properties. Okay, so all this information is present there. Now, the issue here is how we describe the non-local interaction. So the first part is something standard when one does biomechanics in the sense of tumor growth. This would be the new part, how we describe that non-thickened diffusion, how we do that. So in our case, we took this idea from a work in neuroinformatics because they need to. So if you are in Cartesian world, we measure the distances as a real line, The distance between me and you is a line. We are points. We compute the difference. But if you have a change of shape, you need to take into account that. So the geometry needs to be taken into account. And that is done in this informatics. So if you measure your temperature here, how you put that same map here, which is more flat, in some sense, how you keep track of the change of metric. So we did it in a mathematical term, but then we say, no, this is too complicated. Let's go to the Cartesian one. But this is something you can do, It's to say, you can try to do definitions more general than the ones, and you need to use a concept from differential geometry to get these things. Okay, so flat Cartesian distance between 2 points. Why we need the distance? Because we need to take into account if I put a source of something here, how that is felt here. Okay, so how the diffusion in one part influences the diffusion in other parts. This is our scope. So we take the difference for measuring distances, in this case, which are, we have a Cartesian word, and that means that our formulation of non-local diffusion, so this y here is what we call the mass flux vector, okay, the flux of mass. And in this case, instead of its law, it's represented by this integral, so it's already non-local. And we have the kernel measuring the force of the non-locality. Okay, that would be the idea. We pull back that, a lot of things going on there, but the most important thing of these equations is this one. Why that? Because now we have a type of non-locality that is changing with the dynamic of your tissue. So it is growing. I have two initial points at a certain distance, but if we are growing, we need to keep track of that through the motion. Okay? This is the most important thing here, which is the new part, no? The novelty, which is the type of non-locality that changes with the dynamics of the tissue. This is what we are trying to do, not only measure non-locality as static. And that is reflected also in the diffusivity. So you have some x tilde here, I don't know if you can see it, and some x, these are the 2 points. So your diffusivity also takes into account that kind of information of non-locality. So again, we make some constitutive assumption. One simplification is that our diffusivity wouldn't depend on the 2 points because we need to take that from the literature. And we leave it as a 2 points tensor, we don't have any information. So to take things from experiments, we say, okay, let's just assume it is only a function of the points and positions. And then we go to some lab, there are people measuring these things there, and you tell, give me what would be the diffusivity in that case. You take, you put it there, and you have something, okay? So, and this is how it looks like here. Since we are in a biphasic medium, we need to take into account that it's happening on the fluid. Okay, so we need to weigh that by the volumetric fraction of the fluid in that case, which makes, when you do a pullback, it interacts with the dynamics of growth of the tissue. So these are the equations of the model. So we have, again, proliferating cells, how they evolve, how it grows, how nutrients also evolve, no? And you subministrate nutrients to that tissue. What is the pressure? You can find it. And then what are the stresses of the displacement? No? You have all those equations to find those unknowns. And then you go to theories of population dynamics, okay? And you say, okay, this is how you are going to interact, the constituents there. For example, we can look at one simple, so the last one, explain, which is the rate at which proliferating cells become necrotic. How the cells die, how I tell the, because the mathematical model, no, we in some sense are got here. I tell you what to do with the mathematics. The idea is that if you go below, so this operation is just to take the positive property, which means if you're negative, you're 0. What is inside? If you're positive, I return the same value. So if you have sufficient nutrients, it means that you won't die. No, you have food, you eat, you proliferate, you grow, and nothing happens. If you go below a critical value, so the minimum you need to eat to proliferate, then you become necrotic because you are below that minimum. Okay? So this is how you tell these things to the model. You go here, you use mathematics, and you try to. So this is like making some input on mathematics, you know, why they are important, but sometimes we don't see it. And we can also relate to stress, how stress influences that, so which is mechanotransduction. So you can have this kind of information inside your model. So possibilities are many. You just have to choose what you want to do and concentrate on that. So we need to solve that, and that is very complicated as it is. Because here, remember, we have this y alpha, which is an integral. So we have an integral differential equation there. And it's not easy in a nonlinear setting to solve. In fact, if you go to the numerics, there is an issue there. So if you have done some numerics of partial differential equations, usually you are going to solve these bilinear problem in which your stiffness matrix is three-diagonal. So you have only values in the diagonal or the same. But in a non-local approach, that stiffness matrix is going to be denser the stronger your non-locality is. Okay, so what that means that you have a matrix that could be a very big matrix with all the values to be non-zero. So how solving that is not numerically is difficult, and you need to do certain things. In these cases, those matrices are good enough. So they are symmetric. It can be found if you use a nice approximation. You can do some simple computations analytically. You can prove some kind of nice properties of these matrices that you need for the existing to for the solution to exist and to be unique and these kind of mathematical questions. Okay, so now we want to solve that. Since this theory is biological motivated, we want to be describing something in real life. So we assume to have this cylindrical shape. It's a tumor in cylindrical shape. And this could be seen as the avascular state of ductal carcinoma, which is a kind of breast tumor, okay, that grows in the ducts. So it takes this cylindrical shape. You do that by putting your motion. And what we want to find is this value u, so how it will grow in the axial direction. Okay, so it's a simplified version. We don't grow in the radial one, just axially. And how the nutrients will affect that growth. So this is our motivating question. One of the advantages of doing that is your problem again, because of the symmetries that you have with the cylinder, will become one-dimensional. But one drawback is that if you do exactly that in your mass flux vector, it's not reflected in your non-locality function. And when you do mathematics, you would like to maintain some certain sense of coherence. Now, if we are assuming symmetry and things like that, I would like not to distort that symmetry, or at least because it's simpler to do that. So we rephrase that non-locality function this way. And the construction is not arbitrary. So we are looking to something. We are looking to the derivative and fractional and integrals of fractional order. So we are going, even though you don't know what that is, I will show the definition in a few seconds. But the idea is we are going to construct that operator in that way, because it has been used in the past to model that kind of situations. We only need to find that normalization factor there. Okay, and how we do that? So we think about this. I want limit cases. I have that alpha that moves between 0 and 1. And I would like, when alpha tends to 1, to have a standard diffusion, go to a limit case. And then when alpha tends to 0, I would like something, but I don't know. I need to figure out what will be, depending on one of the restrictions that I want Fick diffusion in what limit, okay? So how you do that? You use the Fourier transform for doing that, because it's allowed to do computations. And if you take the limit when alpha tends to 1, if you choose the normalization factor, or in this way, or in this way, you end up in Fick diffusion. Okay, so you have two possibilities doing this analysis. Okay, and then what would be the best one, no, at least from the modeling point of view? So let's say, well, let's go to the other limit, no? When alpha tends to 0. What happens there? If you take the first option of normalization factor, that helps you also with the length, the physical units of the problem you're solving, you see that that is 0, which means that you don't have diffusion. So you go from continuously from no diffusion to standard diffusion. That is a good thing from the modeling point of view, because I see a lot of cases there. And if you do that, mathematically, you go and find that is what you are defining is not something random. It is what is called as the Caputo fractional derivative, which is very used in fractional calculus. Okay, so choosing something wisely gets you results that in mathematics exist. Then you say, okay, but I want to continue my process of thinking. Let me see what happens to the other part, because it's reasonable to also to have that. But when you make the limit, mathematically it has sense, but then you say, okay, what I want to model, no? What is the physical explanation for this? We don't know. It's just that. That would be the diffusion when the alpha tends to 0. So something that is non-zero. I prefer the other because I go from no diffusion to standard diffusion in that way. So you decide. This definition would also give you something called risk potential in mathematics. Okay, so still mathematically have a sense, and then you decide because of the physics of what you are doing. And thus we continue with this kind of form. So when we choose that normalization factor, we end up with this writing of this is how the vector, the mass flux vector looks like in our case. So this is what we need to solve. And you see here that the dynamics is changing the non-locality. So this norm here, to the power of alpha, is telling you how stronger or not is the non-locality, how it will be felt in other points. And that's what varies with this alpha. If you ask me for what is the physical meaning of that alpha, so the short answer is it is another parameter you have to explain your experiments. That would be the short one. That alpha could be related to the internal structure, and this is something we are working, but it's very difficult to explain in a mechanical sound. So you can, as a mathematician, you can do whatever you want at the end. But if you want something physical, then you need to go to engineering or biologists and say, look, I have this, but I can do what I want. Mathematically is correct. What I need, give me some experiment. Okay, I will try to do that. So our idea is that alpha also depends on the microstructure and, for example, tortuosity of the veins. But this is something we're working with. So today I didn't bring any example of that. And so you need to solve that. And you put that in our case, we put it in console. So we pay a lot of money for that to do the job, but we don't trust too much in console. In the sense, we would like to have our own software and things like you do here. That would be better. So what this graphics means. So let me turn to the one at the left. So we have dashed line and solid line. So dashed line means the alpha is near 0. And what should expect? No diffusion. Alpha near 1 is standard diffusion, and we expect that. No? So you see the diffusion here. What's happening here is that diffusion is concentrated at the boundary of this cylindrical specimen you have. Okay? So by fixing that parameter, you tell your model where you want the diffusion to take place. And this could be useful. I don't know still, but it could be useful for drugs. For example, I want to go there. That is the place. Okay, you can introduce electromagnetic forces and nanoparticles to guide the particle where you want to put the drug. Something like, it's very difficult. It's not something easy, but it's the kind of ideas we are searching. And then this is reflected in growth. For example, this is displacement at each point. And you see that when alpha is near 0, in which diffusion is only confined to the boundary, you only grow there. You don't grow in the inner points. Those are consuming nutrients without replenishment, because you are like injecting nutrients to the tumor, but they remain there. Why? Because it's very tortuous, for example. So they have obstacles, and they cannot pass that. And that could be a reason. So you can go from these two kind of behaviors that could help you to design something for a treatment. Okay. And in fact, we try to explain some of these things in biology. And what happens when alpha tends to 0 is that your pressure becomes negative at the inner points. It's cannot be seen here, but the dashed line again is alpha near 0. So you are called positive. And what that means is like a syringe effect. It's like fluid going in the opposite direction, something like that. Why? Because you have limiting diffusion to one place. The nutrients, the cells in the middle are consuming without replenishment. So nobody's giving a truck of proteins or whatever to get you grow. So they will die because at some point that food will finish. You don't have replenishment. They die. They become necrotic, and necrotic cells become part of the fluid. So it's like putting a rock in a lake, and then you create the other wave, no, in the opposite direction. So this is how, with one parameter, in this case, we are recreating that kind of situation that we see here. So mathematics, you can explain that with mathematics. It still needs improvement, but it is how you try to go and explain things in biology using mathematics that we know have been useful in the history. No? It's not that bad. Okay, so that would be it. Thank you very much.
Okay, so thank you very much for the introduction. Actually, it's probably right now my students understand why we make so much emphasis in terms of
Yeah.
well, actually, it's very interesting because in the first part it's very related to kind of research we are doing right now. Because the first part of the research is related to mathematics, and you know, for basically mathematics are structures that have an internal. Basically, have.
Yeah, it doesn't.
Okay. Okay, mathematics have an internal structure, no, and that the internal structure we can build minus cognitive, for example, we are thinking. But right now the idea is not only to have an internal structure and keep moving that internal structure in space, but also keep changing that internal structure. And that's a problem that has not been solved, how to compute continuous properties for that kind of structure, that kind of material. That's very important. So as you know, we are engineers, we need to relate with mathematicians for the Torres. And also the other part, the second part of the project actually is more related on iPhone.
Yeah.
we have a project right now actually the reason of glioblastoma, it's cancer in the brain. And one of the topics we are trying to model right now is basically the change of pressure that is in glioblastoma, and how that helps or avoids that the chemicals change over how we can also stress and the chemical factors. As you see, it looks like may look like far from engineering, but that's what many engineers know. I'm sure that this is so I think that you want questions over any of the two topics or experience in life that's also very interesting. You tell me much.
No, I avoid that.
Well, I can have a question on the presentation. Yes, I did have a question about the presentation. Other than the benchmark problem that you solved, have you done any other kind of test to verify the accuracy of the results obtained with this method?
No, because so as you see, the year was 2018, so we are 2023. So the first thing is because of computational issues, in the sense, so experiments and computational. We don't know where these experiments can be found, so we don't know how to relate to a very specific case, because so the first thing is that the evolution law should reflect the kind of experiment you're doing. Here I show a very general one, but if you would like damage, then we can rephrase all of these in the case of damage and do an experiment and then try to damage in a composite in that sense, and then try to do all the numerics. But at the moment, we don't have now, so that's why I'm trying to come here to people doing that can do experiment. I wouldn't break everything, so I wouldn't know how to do that. And so I have two things to say. That was the first one. Could you repeat the question? Maybe I remember.
Yes, I asked that if other than the benchmark problem that you used, if you have used any other kind of experiment or any other data to verify the
Yes, yeah, I remember now. Yeah, the other issue is the computational framework. So I'm not aware of software algorithms, the code, able to do this homogenization thing in which you need to match the scales. So when we did it, we need to trick console in the sense because it doesn't know how to do that. We need to create some kind of trick to say, solve me this problem, even though you don't know you are solving this problem. And it only works in one dimension, that trick. That is the thing. So if you go to higher dimension, it doesn't work. So we need people that do those codes to help us to then put it in a real life application. So that is always the main idea about it. It's quite difficult. It's not something you do in 1 year. You need like a lot of people behind working together in one problem. But yeah, that is the main goal. The main goal is to go and put it in a real life situation.
Questions? Working that you are
The first part of the presentation, you introduced the concept of assuming that the material was homogeneous, so that macroscopically the ceiling was isotropic material, and already using the main parameters and the traditional equations. And you said that assuming non-homogeneous materials presents a higher difficulty. Let's say, for example, using isotropic or orthotropic materials. Is that a current line of development, or is that not a
No, that could be done. So the same things can be done if you have a triclinic or so other crystal symmetry there. It just was an assumption of simplicity, just to not complicate things, but the same methodology and some of the equations. So some of the equations I show are for any kind of symmetry, except for, so it arrives until monoclinic, I think. So you can put there, this one, for example, here. This is independent on the, so you see there is no Lame parameters, there is nothing there. It's just give me your elasticity tension, whatever that would be, whatever the symmetry. This is how you compute it. So that could be done.
No? People? No questions? You don't have any questions?
Hey, to the
Yes, everything?
you should have questions.
Okay, I would like to ask you about the composition of the information gradient. At the first, you wrote FP, but, and then for the second, you wrote FE.
Yeah.
Yes.
So the main idea is you can put.
And would you consider further decompose the FP? And you said of writing it only as the
So the main idea is that you can use this. You can change the name of Juan and Carlos, and then say what they are doing. But you can combine all of them. So F equals to FE, P. Let me put in this order. F gamma. You can have, which means that you have growth, and that growth influences remodeling or activates or whatever, and then you have the elastic accommodation. You can have the whole path. I just this for it's a modeling assumption in which you say I don't have remodeling, I have growth. You turn off and turn on, or I have growth, I don't have growth and have only remodeling. Or you can have both, all of them, and we have a word in which we have all of them in that case. So remodeling and growth acting together, and how that affects. It was also in the case of a tumor, but could be for cartilage in which you have fibers and you want to build that tissue. So you need to know how these fibers affect the property and how can you build that kind of what you need to do. And the mathematics helps to do that. But you can have all of them, or just turn off and turn on one of the other to separate contributions.
Thanks for the presentation. It was very clear on a lot of stuff, but very clear. I was wondering because the last year we did a research work regarding to hypothesis analysis, and we need to deal with the big equation. So the problem is that it can become as complex as you want, but the computational cost is
Nightmare. Yeah.
so we decided to go for a very simplistic approximation of the big equation that runs only a few seconds and allow us to do a 3D model of the structure of the tool. But at the end of the day, I was wondering what we have lost in our way. So just to ask you if you know or you have done what is why is worth it to go for a very complex formulation of the Flick equation in the tumoral environment, or yes, at the end what we are losing without looking at the high complexity that the details of the Flick equation may have in this environment.
That is a tricky question. So. So the idea is that sometimes just simplifying things, you get what you want, and in a very good approximated way. So, for example, the part in which I say the skew symmetric part of LP would be 0, if you don't assume that, you have a very complicated equation, and then you don't get too many differences. And that happened to us with in a work we did in which we tried to put a gradient theory for plasticity, because we imagine this case in which, so the tumor, there is more proliferations at the boundary. This is where the action is taking place. So if you have a very thin line where this remodeling or this proliferation is very active, then it's like shear bands. No, we imagine that as a shear band, which you need a higher order derivatives. We did this following work by Anand. At the end, we didn't find any difference. So, which means that we complicated the problem. And the first thing to say, maybe the benchmark was not the best one. That could be the case. And that would be the issue. Or maybe reality, we think it's the benchmark. No? Maybe just simplifying things gives you enough information to know. I think in the case you speak, what is the value of the results you obtained? Did you obtain what you expected to, or was not good enough? Because in that case, I will say, okay, we need to go further and complicate things. Sometimes people don't want that, avoid the temptation to complicate things, but sometimes it's even necessary. And computational is very expensive. So one way I could see computational to reduce that is the asymptotic homogenization, because that is the main idea. It was born for that, for people that they don't want to use computers. No, but now the combination of both of them could give you a lot of value, because you can complicate your geometry, but have just one cell problem that you can solve and have very, 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 very complicated geometry. And for example, I know that for virus, how a virus diffuses, having a very complicated geometry is very useful to know exactly what is happening. I don't know specifically what happened there. Maybe we can speak about it later on. You can show me. But I would say I would keep in mind that I had what I wanted, and it's good to know, and we have experiment explaining. So sometimes you can avoid complicated just for the sake of complicating things, get near the reality. Sometimes it doesn't matter. I don't know exactly where would be, but could be the case. I like the complicated things.
Thank you so much for your talk. It was so interesting. Despite all the questions,
I know.
or brought a physical into
If I don't see equations, I don't know what that means, so I have that mind.
but they made a lot of sense because of the physical education that you got, so it took a lot of. My question is more related to the personal life thing.
Okay.
Because I have to say that I was so surprised about the fact that you pursued a second PhD. And well, as a PhD student, and there are several PhD students, I have the feeling that I'm now in my third year. I have the feeling that I'm continuously saying, "Oh, I wish I knew this like 1 year ago," or "I wish I could have known this in the first year," and so on and so forth. So my question is, in your second PhD, did you use some tricks or hacks that you learned or the mistakes that you made in the past in your first PhD? Did you use it and how? Which are those? So could you give us like some advice on this question?
Okay. So let me start saying that the decision to do the PhD was not trivial. In the sense, it was not like I want to do a second PhD. It was life in that sense. So if you live in Cuba, you are isolated in some sense. We are an island geographically, and then we have a lot of things happening there. And for example, when I did my PhD, my bachelor, and my master's degree, we didn't have internet. So forget about internet, that didn't exist there. It was like 16 kilobytes per second in 2012. So you could imagine, no? And I have this experience of for a paper, for example, when a revision came, I needed to go to the university because it was the only place I had an internet connection. Download the review, go to my, I had a laptop, it was like a desktop. Work on the review, go again to the university, send the email, go again. So it was like a nightmare in a place we don't have very good transport. So it's very bad in that sense. So what I'd say this because one of the decisions I made for the second PhD was one life which you want to continue with the postdoc research. I didn't want to go to the industry, to be honest. I had explained I invest. No, it's like an investment. I invest a lot of my time for pursuing an academic career. I didn't want to go and just put that under the floor. And that would be one reason. And the other reason, when you are in Europe, you have a lot of opportunities and you are not aware of. Probably you don't know connections, speaking with people, not being isolated, going to conferences, and things like that. This is something very, 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 very unusual. Unless we have one in Cuba, that would be the only way you can participate. There is no other way. That would be no. So in terms of so my second PhD, because of the relationship I had with my advisor, it felt like a postdoc. So it didn't feel like a PhD. I had to do the courses, but I learned that the courses are not the most important thing. You need to do courses because it's part of the PhD. This is how it's structured. Sometimes you learn, and sometimes you do things like discrete differential geometry that I think I never will use in my life, but I needed to do it. I learned. That's okay. I mean, cultural thing. It was less stress in the sense that I know how it works. I do the courses, I get my notes. Doesn't matter. Nobody in the I think I don't know how it works here, but in the Bible, nobody will ask you what do you obtain when you do the PhD courses. I think nobody cares. The thing is that you go there to learn and to take the most of it, and you don't worry about too much. You need to polish, and that is part, and that comes. And sometimes, for example, since I changed a little bit and I started these things of functional calculus thing, I spent like 1.5 years to publish my first paper in that second PhD. But it was fine because it was a complicated thing, and sometimes quality beats quantity. The beginning, maybe not. Maybe you need quantity for grants and PhD scholarship grants. But then people will tell you, give me your 5 best papers. If you have 50, it doesn't matter. It's 5. That's it. So in that sense, so less stress. Other country, other kind of degree, but at the end it's all the same. So publish. Your supervisor should know what you're doing. Don't stress him too much or her, because he is aware of what is happening more than you, probably. So that would be. It's not Hakuna Matata, but yeah, no, to dive in the attempt.
The answer to your question, my grandmother used to do them. I wish I were as young as you, but no, I'm not. And you know too much your so, any other question? Okay, so I can just
Thank you.